Oh,
Hi, Professor. My name is Venkat Ajay Karla. I'm going to continue the remaining part of the PPT. So now, finally, if the transform program is sliced with the respect to the final value which we get from the robust variable once more, then the like we call it unnecessary things like the assignments to the variables we have created before the x, bc, and sc, and the result will be removed to make the step 4, which will be explained the next. Here we have taken some example for the step 4, which is a non-conventional slice. So first I'll assign like a constant value like 1 to the robust, and I'll take an input from the user as a source, and I'll take the I variable as a 0, and I'll run the loop till the I value gets to the 128, and then I'll assign some value to the robust, which is the robust value from the above, and the I value greater than 0. I'll make a logical end operand from here, and with the I less than or 127, and I'll take some value from this expression to the robust, and now I'll increment the I value. After the loop exists, then I'll make I as a 0, and now the robust becomes the robust value, and the robust will be assigned with I greater than 0 and I less than the max, which is a max value, which we assume the largest value. And now I'll take a while loop with the source I have taken the input, and I'll make it as an array with the I value, and which will be not equal to the backslash of 0, so which is like a null value, and I'll run the loop. So with the robust value, I'll assign again the previous robust value with the logical and operand with the I greater than 0 till the I less than or the max value, and again I'll take the source array with greater than or equal to 0 value, and the source of array with less than or equal to 127. After this expression done, then the value will be assigned to the robust. Then I will increment the I value again, and I'll assign a I value with the character A. After that, again I'll run a loop, the while for which I was less than 120, like till 127. Then I assign a robust value with the previous robust, and the I greater than 0 and I less than 127, like, and then I'll increment the I value. Then I'll again assign a character A to the I. After that, I'll run the same expression, but I'll take till the character Z. Here, the 128 is the ASCII value for the Z. So now, I less than I'll take, for now, I'll check with the original character with the I value, which I have from the above. So now I'll run the same expression as robust with the robust of AND operand to the I greater than 0 and I less than or equal to 127. Now I'll increment the I value. Here, the step for which I have explained before is not a slice in the conventional sense of the word, but here it is a non-conventional sense. This is because the transformations which we have done and all the semantics we followed preserving may not be the syntax preserving. So they do not simply delete statements from the original program, rather than they just replace the original statements with the equivalent statements. Yeah, and now a motivation for the robustness slice approach which we are going to take. So here the robustness is not a property of program which can generally be computed, because the proposition or the program P is robust, is undecidable. Yeah, we cannot measure the robustness. That's what this means. And to see that the robustness is undecidable, consider the following code fragment. The fragment is a schema or a structure where the f1, g are the arbitrary functions, and a is an array which we taken, and the maximum permissible index of which is the maximum, which is the utmost value which we can take, and we'll take an input of a variable x from the user, and we'll check the statement of the f of the functions with the two functions, the f of x and which is not equal to g of x. If they are not equal, then we'll assign the array A to the array of max value to the 10. So till we can make the 10 steps. this fragment will be definitely be robust. If the two functions f and g happen to be equivalent, then 8 times of f of x equal to g of x and will definitely not be robust, and if f and g are not equivalent. This is the one condition. And therefore, if there exists an automatic procedure for deciding whether a program is defined definitely robust, there shall also be an algorithm to decide whether two arbitrary functions are equivalent. And there is an algorithm explained in the further slides. So as the question of the whether two arbitrary functions are equivalent is known to be undecidable, the robustness question must likewise be considered to be undecidable. A similar argument demonstrates the undecidability of the other implicit computations listed in the section 4. If an attempt is made to implement a system for automatically deciding the robustness, the user of such a system will therefore have to be content with a yes or no, maybe or may not be response. And the undecidability of the question of robustness will often mean that such an implementation will answer the maybe, and there is no approximate or accurate value. We only have the approximate value. We don't have the accurate value for the robustness. This is what it means. Yeah, the robustness slice approach avoids the issue by returning a program rather than attempting to produce a the negative answer to the robustness question. Ideally, the algorithm for constructing a robustness slice will produce the program fragment as a robust equal to 1, signifying that the subject program is robust, or it will produce robust equal to 0, and signifying that the subject program is not robust. In maybe cases, however, the algorithm will approximate the complete yes or no information by producing a simpler program which stores either 0 or a 1 in the variable robust as explained above, but which do so using more than one program statement. Such a maybe program constitutes an approximation to the two simplest programs. Using the robustness slice approach, it will thus be possible to produce complete information in the cases where robustness characteristics can be computed, but with the significant bonus that where such information may not be computable, the algorithm shall be able to assist manual analysis by program simplification. Yeah, the term robustness has different meanings depending on the field of application. In robust optimization, or which we call as RO, and the robustness is related to the decision or solution itself. It's the capability of algorithms solution of coping with the worst case without losing feasibility. In machine learning, we know, especially in a deep learning, robustness is related to the learned model, which will be learned from itself. It is the property of the model, the deep neural net, that is the deep neural network, DNN, that determines its integrity under varying operating conditions with the different types of situations. The others are the first to discuss robustness in the DRL context. They propose to use genetic algorithm to improve the robustness of a self-driving car application. Robustness is considered as the capacity of sustaining a high accuracy on image classification, even when we perceived images change, and it is measured by neuron coverage. That is the ratio of the activated neurons in the deep neural network. There are only a few recent works on the robustness of slice placement procedures, most of them on the RO. These works answer the question different from one we are investigating, as they evaluate the robustness of the decision, whereas we want to evaluate the robustness of the learning process. Despite their originality, the above approaches present some drawbacks, such as the lack of scalability of ILP, the suboptimality of heuristic solutions, the fact that they consider offline optimization in which all slices to be placed are known in advance, and the fact that they are single objective optimization approaches, mainly focusing on energy consumption minimization. In this work, we propose to rely on DRL based approach in order to overcome the ILP and heuristic drawbacks and consider multiple optimization objectives. However, the others focus on the evaluating the robustness of the DRL approach against random topology changes. Example, node firewalls or deploying new nodes in the network topology. In this work, we focus on evaluating the robustness against network load unpredictable variations. To the best of our knowledge, the present work is the first to perform such an evaluation. Yeah, and the remaining slides will be explained, my friend.